Samson is one of the most lucid and compelling speakers I've ever heard. When he talks, it's like this uninterruptible flow. You get caught up in it and you have no idea when it's going to end. So in order to signal the end, to make sure we don't forget. Okay.
That's discriminatory behavior. Thank you very much. So, I note according to that clock we are slightly...
Noted.
Right, so since there's been a lot of material previously about the general setting for this talk, I'll try and be relatively brief on that. Was it return?
Up and down.
Up and down. So the context is provided by the sort of program of categorical quantum mechanics we've already heard about in a couple of the previous talks today. And the general idea there, as we've heard, is to use monoidal categories and various structures within them, such as compact closure, Frobenius algebras, and so on, to axiomatize substantial portions of quantum mechanics. And this then provides a basis both for high-level reasoning, calculations using graphical methods of the kind that we've been just seeing, and also exploring various foundational issues in what I think is a very interesting way. So I'm not going to talk about that in generality here, but there's a sort of point arising out of that which sort of leads on to the work I'm going to be talking about. And by the way, I should have said that the work is joint with Chris, one of the organisers of this workshop. So there we are. So the point of departure, so to speak, is that these structures, notably compact closure and Frobenius algebras, only have finite-dimensional realizations in Hilbert spaces. You can only have a compact structure on a Hilbert space that's finite-dimensional if and only if, and as we'll see in a moment, Frobenius algebra implies compact structure. So this raises some obvious questions and challenges. I mean, is this an inherent limitation for these kinds of methods? I mean, does it matter, perhaps? But it seems to, because things that go beyond finite dimension certainly play an important role in physics. So, rising from that, a sort of a fairly straightforward question, motivated question, is to find a good general notion of Frobenius structure which works in the infinite dimensional case in Hilbert spaces. And then, as we'll see again shortly, one of the main uses or roles of Frobenius algebras in categorical quantum mechanics has been as a nice algebraic way of describing bases, orthonormal bases, and observables in quantum physics. So going along with the idea of having an infinite dimensional version of Hilbert of Frobenius structures is that we should then be able to describe more general bases and observables. And of course we want to do this not just for Hilbert spaces, but in this categorical language, and extend the analysis to other categories as well. And another goal, sort of going along with that, is just to clarify mathematics that's going on here and relate it to the wider literature. One might expect there's a lot of stuff out there, and indeed there is. So in the work that we've done, I think we've accomplished a fair amount on this in this direction, although, as we'll see, an intriguing problem remains open. So if anyone knows the answer, shout out at the end. So very briefly then, because we've already heard various presentations of this material, I'll go through some of the background. So we have the general setting is dagger monoidal categories. So a dagger category is a category equipped with an involution, and think of the adjoint in Hilbert space, or think of relational converse in the category of sets and relations. And then, we've already heard these things before, but we say that an arrow is a dagger monic if it has this, if it's inverted on the left by its dagger, and it's a dagger iso if both of these things are dagger monics, if you get both, if it's a two-sided inverse. A dagger monoidal category then combines in a coherent way a monoidal structure, and for us we'll always be working with symmetric monoidal structures where the tensor is a dagger functor, it preserves the dagger in the obvious sense, and the natural isomorphisms, the structural isomorphisms are dagger isos. And the examples immediately are in Hilbert spaces, which for us is going to be Hilbert spaces of arbitrary dimension and bounded linear maps, and rel, the category of sets and relations. So Hilbert spaces with the usual tensor product, dagger is adjoint, and relations, dagger is converse. In Hilb, the dagger isos are exactly the unitaries, and dagger monics are isometries. So we recover familiar and important notions directly from this little abstract language. So again, we've seen this quite a few times already. Here's a diagrammatic language or graphical calculus for symmetric monoidal categories, absorbing the tensor into the topology of the plane, so to speak. But we're dealing with a symmetric situation, so we'll allow crossings without preserving the information about what goes over what. We're not working in a braided setting in this particular work. Dagger diagrammatically, again, we've already seen this. We're sort of using this convention of clipping the corners of these boxes to tell us which way the arrow is pointing. We can represent the dagger by 180-degree rotation. And then here are some examples of equational laws expressed diagrammatically. These are just the defining properties for dagger monics and dagger isos. And again, we have the important case where an arrow comes from nothing. This is the tensor unit, so we can write it as a triangle in this fashion. So we get the notion of state or ket or point, which is an arrow coming from nothing. A Dirac bra or a co-state, a co-point, is something that goes in the other direction. And we can compose these to get a version of inner product. So the language of dagger is already immediately gives us a notion of inner product, where the scalars are taken to be the endomorphisms of the tensor unit. And in the case of Hilbert spaces, the tensor unit is the complex numbers, and a linear map from the complex numbers to itself is uniquely defined by a complex number. So it's the right kind of thing. And indeed, this gives a kind of two-dimensional generalization of Dirac notation, as Bob was mentioning in his talk, where you also get it combines gracefully with the tensor structure as well, because you have two dimensions to slide things around in. Okay, so in this setting, we can formulate the notion of dagger Frobenius algebra. Frobenius algebras, we heard extensively in Bertfried's talk yesterday, are a classic notion in mathematics. A particular form of such algebras were introduced in this general setting of dagger monoidal categories by Bob and Dushko Pavlovich in their paper on quantum measurements without sums. So here we're taking this dual structure and we're planting the dagger in there to say that the algebra and co-algebra structure are related to each other exactly by one being the dagger of the other. So the way that they presented it, you take as primary the co-commutative co-monoid structure, this co-multiplication here, with its co-unit. We also saw this in Charles' talk yesterday as well. But now we can, and then these are the axioms for a co-commutative co-monoid written algebraically. And then we have two additional axioms as well, which is saying that the delta is a dagger iso, and that and this Frobenius equation written algebraically like this. But let's immediately pass to a diagrammatic presentation. So again, we've seen these diagrams already, so we don't need to dwell on them. We write the co-multiplication just with a dot like this. I think that's consistent with what we've seen. Here's the co-unit. And then, following our convention that you get the dagger is portrayed just by turning things upside down. So here's the, then indeed a multiplication is just going to be, in our convention, since our arrows are going up, is going to be something that turning one of these around to point downwards. And here are the co-unit laws, co-commutativity and co-associativity. So you get the very same things, just turning it around to get the usual monoid, commutative monoid axioms. Dagger monic is just this, and here is the Frobenius axiom portrayed diagrammatically. So when a multiplication and a co-multiplication meet, in this order, they can be rearranged in this order. And I haven't written the symmetric one because we have a commutative situation here. And really, the import of this is that it's a normal form theorem. It's telling us how to slide co-multiplications past multiplications in such a way that in the end we we end up with a bunch of multiplications facing a bunch of co-multiplications. So there's a very nice normal form that arises for, a well-known one that arises for Frobenius algebras in this way. Okay, now why are these things important in the setting of categorical quantum mechanics? Because they provide a high-level algebraic way of talking about orthonormal bases and hence observables in quantum mechanics. So as we know in quantum mechanics we have the no-cloning theorem, which says there's no quantum evolution which perfectly copies an arbitrary unknown state, makes two copies of an arbitrary unknown state lying on exactly on the diagonal in the tensor product. On the other hand, if we are given a particular basis, and this is in any dimension, we have no problem in defining a map on the basis and then extending it to a bounded linear map on the whole space by putting the basis on the diagonal in the tensor product. Of course, when we take that linear extension and apply it to an arbitrary vector, it will certainly not give you two copies of the vector you started off with. So this is perfectly consistent with that. But what it's saying is, for the basis vectors, for a given chosen basis, we can perfectly well copy them. So this leads to the idea that you can treat a given basis as a certain classical context, and therefore the basis vectors are, so to speak, classical data in that particular context. This is familiar in quantum computing, where you have a chosen computational basis, and as long as you stay on the basis, you're essentially computing classically. There's also a deletion map. Whoops. There's also a deletion map, and this is the co-unit, and it's allowing you to erase any vector on the basis, and then it extends linearly to the whole space. But this one is now strictly only for finite-dimensional spaces. It gives you something well-defined only for finite-dimensional spaces. So this is sort of point of entry to see why that has to be shortly. So here are two striking results in finite-dimensional Hilbert spaces. Orthonormal bases on the one hand, and dagger Frobenius structures as we've defined them here on the other are in one-to-one correspondence. We'll give a more mathematically structured version of this shortly, but that's how the result appears there. And another result by Pavlovich, that in the category of sets and relations, dagger Frobenius structures correspond to disjoint unions in abelian groups, which looks like a very different result, but also suggests that it's not as different as you might think. The problem is that this notion of Frobenius structure as we've defined it, which requires a unit, limits us to the finite-dimensional case in Hilbert spaces. And in fact, a Frobenius structure on an object always gives rise to a compact or rigid structure where the object is its own dual, on the given object, where the object is its own dual, and we know that that can only live on a finite-dimensional Hilbert space. So we can define, for example, either a unit or a co-unit out of, in the sense of rigid structures or compact structures, out of the co-multiplication and the unit here, or dually the multiplication and the co-unit. And then from that and the laws of Frobenius algebras, it's easy to see that this does really give you the typical yanking law that we associate with compact structures. So it's an equational consequence of the axioms of Frobenius algebras that from these definitions you get a compact structure. Okay. So I won't go through that. Now, let's remember what the axioms are. We mentioned these before. I'm going to itemize them here. So associativity, unit, commutativity, this dagamonic axiom or specialness of the Frobenius algebra, and the Frobenius axiom itself, F. So we're going to, given so to speak, the diagnosis is that it's the unit or co-unit that causes the sort of restriction to finite dimensionality, we're going to redefine a Frobenius structure in a dagger monoidal category to be an object equipped with a co-multiplication satisfying these properties except for, so we're not assuming a unit, and it satisfies all the axioms other than the unit or co-unit law. So that will be the general case of Frobenius structures for us. The one that does have a unit satisfying the unit law will be called unit, to make that sort of special case. And as we've just seen, unital Frobenius algebras allow us to define compact and hence closed structures. So the question we can ask is, and that's never going to work on infinite dimensional Hilbert spaces or anything like that. In fact, the only, as far as I know, the only examples where you don't get some kind of finiteness condition, where you have compact structure, are very discrete set theoretic kinds of structures, such as sets and relations or similar things, and where you still have a compact structure. So the question is, how much of this could we keep in key examples such as Hilbert spaces? So it's interesting to probe this a little. Hilbert spaces are kind of tantalizing and frustrating, since they do have duals, of course, the dual spaces, which really, because of the inner product, we don't have to think even of linear functionals. You can just think of twisting the inner product structure through complex conjugation. So it's a very kind of first-order notion. And in fact, there's a very nice linear isomorphism between any Hilbert space of any dimension and its second dual. And indeed, there's a conjugate linear isomorphism, a natural one, between H and its first dual. So that all looks very promising for having a duality. But it's not the case, for example, that the tensor unit, which for Hilbert spaces is just the complex numbers as a one-dimensional space over itself, is exponentiable. We can't make function spaces out of it, because if it was, that would tell us that we have a bounded linear evaluation map, uncurrying that. And then we also have its adjoint, and then we have a compact structure. And this is exactly the sort of thing we don't have. Another way of putting it is, one of the big themes of category theory is internalization. So, for example, a closed category has an internal Hom, as one says. You take the notion of arrows between two objects and make it itself into an object that lives in a category. This is a very powerful idea, but it doesn't always work. And this is one of those cases where things don't work all the way. And so in particular, the inner product structure itself, I mean, lives on the Hilbert space, plays an absolutely fundamental role, but cannot be fully internalized. So if we fix one argument, we get a bounded linear map, but the bilinear form is not bounded in that way. So what we're going to do is to present an axiom which captures what seems to be the best we can do in general in the way of a kind of transfer of variables. Because what we're looking for when we look at closed structures is so-called transfer of variables, lambda abstraction to logicians or computer scientists, or if we think of negation of duality, the fact that the knot lets you shift formulas between antecedents and consequence, or assumptions and conclusions. So that kind of transfer of variables, to what extent can we get something like that? Well, of course, we can take a very standard idea. Given a co-multiplication, we also have a multiplication. I'll typically write it now as mu, give it a kind of first-class status, although it is just defined in this context as the dagger of the delta. And we can curry this multiplication for points. That we can do. And this is a very familiar thing in algebra, it's just the regular representation. Of course, we have two ways of doing it, left and right regular, but in a commutative context, we don't really have to worry about distinguishing them. So I think I'm using the left one here. So what does this do? It maps us from the points on A into the endomorphisms on A. So we have a fixed element, x, and we multiply by it using the algebra multiplication to get a map that goes from A to A. So a very standard idea. And this will be, at least if we have an associative multiplication, this is a semi-group homomorphism. So now we're coming to this axiom we want to isolate. In the dagger category, of course, it's always true that the endomorphisms on an object form a monoid, just on the composition of the identity and so forth. But in the dagger category, they form more than that. They form a monoid with involution, with the involution given by the dagger. And we say that this structure satisfies axiom H if there's an operation on points, which I'll write as x map to x star, which such that this very map that we just defined becomes a homomorphism of involution monoids. So this is the defining equation. And if we write it diagrammatically, we see that it's indeed a kind of transfer of variables with respect to points. So we have the x down here as an input, if you like, and it swings up and matches its behavior as an output. So it's a limited transfer of variables available for points. Now, there's a nice observation in this paper by Hooker, Pavlovich and Vickery, which is really the central point in their proof, which can be translated into this setting as saying exactly that, or this language, as saying that Frobenius, the Frobenius axiom plus the unit law implies this H axiom that we just introduced, this transfer of variables for points. So in fact, given a unit, we can define this operation on points like so, co-multiplication starting off from a unit and then putting x dagger in, and we can then compute this transfer of variables using the Frobenius law. So here's our x star down here. We expand its definition, so it's this thing. We apply the Frobenius law, and this is a unit, so we can cancel it, and we're left with this. So Frobenius plus unit implies H. And on the other hand, if the category has enough points, so behavior of maps is determined by the states or co-states you can plug into them. We have daggers, so it's sort of states and co-states can function more or less equivalently here. Then we get the converse. Namely that, or in the following form, that if you have the H axiom and associativity, then this implies Frobenius. So let's see that diagrammatically. Here's, we plug in a point here, and since H refers to points, it's clear we're going to need to compute with points. We use the transfer variable law, the H axiom, to swing this down here. Now we use associativity to rearrange, and now we use the transfer of variables again to put it up here. And if this, since this will hold for all x daggers, for all choices of x, in a well-pointed setting you can cancel off the x and just obtain the Frobenius. And the categories we're most interested in are well-pointed in the relevant sense. Okay, so now let's come back to the question, what actually is the theorem about the correspondence between Frobenius structures in Hilbert spaces and bases? What is the mathematical context for this? In fact, the content of this result is really a very classical kind of structure theorem in algebra. So a real classic of the subject, going back to Wedderburn, slightly later than the work of Frobenius that we heard about from Bertfried yesterday. That every finite-dimensional semi-simple algebra is isomorphic to a product of full matrix algebras. That holds in the general non-commutative case, but in the commutative case over the complex numbers, this takes the form, the algebra is isomorphic to a product of one-dimensional complex algebras. That's exactly what it says, because things collapse a bit. And of course this is generalized by Arthur, and there's a huge subsequent development. Now let's see how that kind of structure theorem relates to this correspondence with bases. So if we have a co-algebra determined by an orthonormal basis, as we've already seen, then really we can think of this as a as being isomorphic to a direct sum of one-dimensional co-algebras. So on each basis vector, you're just mapping into the little bit of the tensor product that lives in that basis vector. So it's just this. So one instance of this, one fixed value of I, is just one of these unique co-algebra structures on the one-dimensional algebra. And to say that a Frobenius structure corresponds to an orthonormal basis is exactly to say that it's isomorphic as a coalgebra to a Hilbert space direct sum of one-dimensional coalgebras. And this is over any cardinality. So, and of course, if we turn this around by dagger, this is exactly equivalent to saying that A is isomorphic as an algebra to a direct sum of one-dimensional algebras. So it's really exactly a form of a Wedderburn type theory. Now, one thing we found looking in the literature is some beautiful work out there that I hadn't been previously aware of, going all the way back to 1945 by Warren Ambrose on the subject of Hstar algebras, where we've derived the name of our H axiom from. What he does there is to show that there is a perfect generalization into infinite dimensions of the Wedderburn theorems in this particular class of Banach algebras that he called Hstar algebras. Actually, his paper was the one that apparently coined the term Banach algebra, because in the Russian school they've been called North rings. So what is an Hstar algebra? It's a non-unital Banach algebra based on a Hilbert space, such that for each x, this should look familiar by now, there's an x star, each vector, there's a vector x star, which satisfies this equation in relation to the inner product. So you can transfer the variable around from one side of the inner product to the other, and similarly for right multiplication. And of course, if we write this out in terms of daggers and tensor products and composition, we see that this is exactly equivalent in a well-pointed context to the H condition. So really, what we've done is to abstract Ambrose's condition expressed concretely in terms of these Banach algebras. So the H condition is the abstract form of Hstar algebras. And by the way, it's worth noting, just because you might say, well, how do we know we're dealing with a Banach algebra here? We've just got a Hilbert space with some algebraic structure in this H axiom. But it turns out that the M condition, the fact, or the specialness of the Frobenius algebra, does imply that actually the algebra must be a Banach algebra. Because the norm, of course, can be defined out of the inner product, taking in a product of an element of itself, which can be defined in terms of the dagger, we can do a little computation here using the fact that this is a special algebra, that the co-multiplication is a dagger monic, and see that this is in fact a Banach algebra. So we're exactly, taking Hilbert spaces as our particular dagger monoidal category and interpreting algebras, looking at the commutative monoids in them satisfying the H axiom, we exactly have the Hstar algebras. That's exactly what they are. So the Ambrose structure theorem, so therefore, well, this just summarizes what I've said. Any such structure in Hilb satisfying these axioms is an Hstar algebra and also satisfies the Frobenius law, because we've seen that generally the Frobenius law is implied by the H axiom. Now, the Ambrose structure theorem in the commutative case, it generalizes the Wedderburn theorem, so it's a more complicated, it's a sort of prime factorization in general in the non-commutative case. And in the commutative case, everything really reduces down. What it says is that a proper commutative Hstar algebra of arbitrary dimension is isomorphic to a direct sum of one-dimensional algebra. And properness is guaranteed again by the specialness, and which also ensures that everything is normalized. Of course, this is equivalent to asserting isomorphisms qua coalgebras, so it's exactly the result that we're after. So this is the answer, but it's an answer to apparently a slightly different question. Now, how much time do I have left?
15 minutes.
15 minutes. Maybe I'll just say a little bit about the proof then, rather than copyable elements. These are the things that behave like basis elements, that are the candidates to be basis elements. So a particular copyable element, in other words, something that lies on its diagonal under the co-multiplication, are exactly the images in our given coalgebra of the unique canonical coalgebra on the one-dimensional algebra. Right? So they're the things where you get a morphism like this. And again, this turns into something more familiar if we use the dagger to turn things around. They correspond exactly to the algebra homomorphisms from this thing into the one-dimensional algebra. And of course, these are the characters of the algebra, the elements of the Gelfand spectrum. Now, we can form a direct sum of one-dimensional coalgebra indexed by the copiables in this way, and this will have an isometric embedding as a coalgebra into into this coalgebra that we start off with. And the question we want to ask is, does the image, so this is a candidate to be an orthonormal basis. It embeds isometrically into the space, into the algebra we started off with, and we'll know that the whole space determines, the whole thing is determined in this way, and therefore satisfies a structure theorem, corresponds to an orthonormal basis, if the image of this thing spans the whole of H. And, the image is a closed subspace. We can project vectors onto it. It'll span the whole space if every vector is determined by its projector onto the subspace. That'll be true exactly if there are enough characters to distinguish any two points. In other words, that'll be true if the Gelfand representation is injective. And that holds if and only if the algebra is semi-simple. So semi-simplicity is a necessary and sufficient condition for this decomposition and hence its representation as an orthonormal basis to hold. So what we get is that a Frobenius structure in Hilbert admits the structure theorem and corresponds to an orthonormal basis if and only if it's semi-simple. Semi-simplicity is a very famous notion in and in fact, what we can say is that the Frobenius structure in Hilbert satisfies H if and only if it's semi-simple, and hence admits the structure theorem and does describe an orthonormal basis. So if H is satisfied on the one hand, the algebra embeds, well, actually that's not the best argument, but at any rate, this follows fairly readily from the things we've already seen. And the converse is easy to see, because if it does satisfy this structure theorem, it's easy to see that such a thing must satisfy the H axiom. You're given a basis, and you can actually define the X by taking conjugate coefficients. And in fact, pursuing this line of reasoning, we found a list of equivalent conditions on a Frobenius structure in Hilbert, which make it nice in the sense that it does give us something admitting this structure theorem and hence corresponding exactly to a particular choice of orthonormal basis. So and we have semi-simplicity, as we've just said. We have the H axiom being a directed co-limit with respect to isometric homomorphisms of finite-dimensional unital Frobenius algebra. So it really is the things that could be nicely approximated by the finite-dimensional ones, and also have a simple form of approximate identity. Now, if we come back to the correspondence result that we mentioned earlier, of course, it's a consequence of the general result and the lemma I mentioned earlier, which shows that the algebra is C-star and hence semi-simple. So as one would expect, it fits in. As a historical note, if one looks at the important thesis by Lowell Abrams on Frobenius algebras and 2D QFDs, and the well-known and nice book by Joachim Koch is largely based on that thesis. In fact, various nuggets there include the explicit observation that in the special case a unital Frobenius algebra is semi-simple, and a commutative semi-simple unital Frobenius algebra is a direct sum of fields. So actually the ingredients are essentially all there, although there's an extra piece of relating it, using the Frobenius axiom to relate it to orthogonality. Okay, so we're building up a nice picture, but we still have a question, as you may have noticed, that remains open at this point. which is, can we close this circle by showing that the Frobenius axiom, without unit, implies the H axiom. If it did, everything would match up in a beautiful way, and we'd have a very nice story that worked in infinite-dimensional Hilbert space. And indeed, we'd like to know that more generally, since all these notions make sense in any dagger monoidal category. So, I would like to tell you the answer, but I can only tell you partial answers. We can say that if it does, then non-unital Frobenius algebra seems a pretty good candidate for the right notion here. If not, should we consider other axioms as things to work with? But as I say, we have partial results but have not solved this question as posed in Hill, which seems quite hard and at the same time also not quite the problem that people who do work in these fields actually ask themselves. Now, let's just say something about positive results. So what we have been able to do is to give a complete analysis of non-unital Frobenius algebra in several cases which are related to each other and which go, so to speak, down the other main branch of models that have been of interest from the categorical quantum mechanics point of view, namely relation-like things. So one class is categories of relations valued in cancellative quantiles. So we take relations but we generalize them so the truth values can lie not just in the usual 0, 1, but in a quantile, a kind of something like a phase space. We heard about phase semantics in some previous talks, but we do need the property of cancellativity. And another interesting case where we can prove a positive result is with an infinite dimension, matrices of arbitrary dimension with non-negative real entries and with the condition that rows and columns are all L2 summable. This contains, as a proper subcategory, the category of real Hilbert spaces and bounded linear maps. So it's quite a big, roomy category, but there is this non-negativity condition, which does play an important role in the results we're able to obtain. Coming back to the cancellativity, as we have topos theorists in the audience, the only locale which is cancellative is the two-element Boolean algebra. This is easy to show. So therefore we don't get, it doesn't go in the sheaf direction, but lattice-ordered groups and cancellative monoids will give examples of. So it's things like the reals or extended reals or the unit interval with its order as a quantile and with multiplication as the operation, things of that nature. And the theorem is that non-unital Frobenius algebras in these categories decompose as direct sums of abelian groups and satisfy the H axiom. So in these cases, F does imply H. So this can be seen as a generalization of the result by Dushko-Pavlovich, which I mentioned earlier, which applies to REL. And by the way, his arguments very heavily rely on the presence of a unit, but there's even a version of the category of relations, which I think in many ways is a good qualitative approximation to Hilbert spaces of arbitrary dimension. So we take relations and we consider so-called locally bifinite relations. So we have arbitrary sets and we have relations which are such that every point is only related to finitely many things, and also also with respect to the complement as well. I draw it like that. So this is a kind of putting a very crude finiteness topology on relations and limiting them in that fashion. And then it's immediately clear that you'll have the same kind of problems with units in those kind of relations that you do in Hilbert spaces when you're in infinite dimension. But the result still holds in that kind of setting, for example. Okay, I'm almost out of time. I'll just say that the proof of this result, almost one proof, although it covers some closely related cases, is quite fun. I mean, we look at a matrix, and the crucial property that comes from the positivity or the quantile nature of the the values that the entries in the matrix are taking, is that you can only have at most one thing which is related to any given pair of things in multiplication. From that, we sort of use the Frobenius axiom so often that at one point we were kind of saying we felt like monkeys jumping on Frobenius typewriters and sort of keeping on using that sort of rule in various circumstances. But using Frobenius repeatedly, I mean, we can show that this naturally defined relation is an equivalence relation. If you restrict the operation to the equivalence class, it's a commutative semigroup, and then using Frobenius again, and this deep underlying connection between Frobenius and group-like behavior that we heard about in Sean's talk, for example, group-like behavior and multiplication, co-multiplications, we show that in fact it's a group. Further applications show that, that it does reduce to this particular form that we described. Okay, so we might ask how different is the situation in these matrix categories from Hill. It's not quite as much as one might suppose. Of course, Hill was equivalent to a full subcategory of the category of complex matrices with L2 summable rows and columns. The only assumption, but it is a big assumption that's not satisfied, is the positivity. Also, the result looks different, but one should beware here because there are some subtleties. If we consider group rings or algebras, which again have been mentioned, over the complex numbers for finite abelian groups, then they give standard examples of Frobenius algebras, unital Frobenius algebras. Hence the general lemma we talked about earlier applies, and they do indeed decompose as direct sums of one-dimensional algebras, and this is in fact well known. But the isomorphism which gives this decomposition may be quite non-obvious, and in particular it might be, for all I know, algorithmically difficult to compute. And in particular the copyable elements are idempotents, so the only group element which is copyable is the identity. So you have to look very hard for your basis in that context. And of course that very decomposition shows that group rings over the complex numbers are very weak invariants of the groups. So the two group rings will be isomorphic just if the groups have the same order, although they may have wildly different structure. But this is very sensitive to the field we're over. For example, group algebras over the rationals are isomorphism invariants of groups, so which scalars you have make a huge difference. And really it's all the same result. So just to finish up, we're still investigating this question of whether Frobenius and the specialness axiom imply the H property in Hill, but more generally. What we do have is the following nice result based on some nice work that Chris has done about on dagger kernels. Which is that every commutative algebra in Hill which satisfies these assumptions has a nice direct sum, Hilbert space direct sum decomposition into a semi-simple algebra and a radical algebra. So the radical algebra is a thing that has no Gelfand spectrum at all. It's as nasty as can be, and the two things separate out like that. And if you think of the isomorphic embedding we had before, that will give us this part. And the question is there anything left over in this part? So the question reduces to, does there exist a non-trivial commutative radical Banach algebra in Hill which satisfies these properties? Well, radical algebras are pretty weird beasts, and the answer we haven't found to be out there. So the question remains open, but that's as far as we've got. Thanks very much.
So, how does this relate to unitarity?
As context, Prakash and I and Rick Blue wrote a paper about nuclear ideals in tensor categories some years back, which was exactly addressing the question of to what extent you can have compact structure and also traces and so on in categories that like Hill and some other related examples. And I have been thinking about those things again. I don't know exactly how that relates to this work, but it does definitely relate to other approaches I've been looking at recently about how one might talk about observables in generality without assuming things like things that imply compact structure. In fact, I think there's a much more general language of observables which should, in principle, be independent of the tensor structure. Because after all, you don't need tensor to talk about observables usually. And I think if you have a trace in the sense of a trace ideal, then that's part of the structure that you need to make that work.
If you look at this in a perspective from a physicist, yeah, you would model quantum systems on an infinite dimensional, say separable Hilbert space, by putting a certain measure which allows you to produce the Lebesgue measure on this space. In which way is your method even sensible to different Lebesgue measures or different type of models? Because otherwise it's a sort of theory which I don't see how you...
Well, I mean, this would apply to observables with discrete point spectra. So things that arise from compact operators.
Okay, if you like, I drop the separable and then you can have...
No, I don't think the separability is the issue. The issue is the different kinds of operators and the different kinds of spectra they can have. Yeah. So I agree that there's a further level where you don't have point spectra and that you have those kind of phenomena. We're not addressing that in this work immediately, but this is the first step to the case, which is already quite substantial, where you have operators on infinite dimensional spaces with infinite discrete point spectra, where this kind of analysis is directly relevant.
Steve has a question.
Yeah, so in Hilbert spaces, when you've got when you're talking about bases and more generally spanning, you've still got the usual algebraic notion of those, but because of the topology, you can also ask whether the closure of the span is the entire Hilbert space. So
yes.
I was wondering which notion you're using.
Of course, the closed one.
Okay.
Yeah, I did mention that at various points, but it was all kind of flowing by. There was the subspace, when we had the isometric embedding, was a closed subspace.
Still a question?
Can you deal with affiliated operators? So
with what operators?
Of affiliated. So lots of observables a physicist would like to write down do not live in the closure. Do not live easily in the closure of bounded operators on a Hilbert space. So usually you affiliate operators to the algebra to get a complete set of observables. Especially unbounded operators of this type.
Yes.
So is there a chance to see that you can deal with affiliated elements?
Well, I think that's an interesting direction. This is a kind of basic question which already has turned out to be quite tricky. Of course, as you're quite right. I mean, the only thing I'll say that's kind of relevant here is that this L2 matrices thing does, of course, include unbounded operators. Not necessarily all the ones. It includes total unbounded operators, and there turn out to be enough of those to make a well-behaved dagger monoidal category. But of course, many of the important unbounded operators are partial. So yeah, once one goes into that world, there could be a lot more to consider. I agree. I mean, this was a very basic question, which was already proved to be somewhat simple.
I guess you have to deal with nuclear spaces or something to do that properly, right?
Yeah, you have to look at the domains of definition.
Yes, so it will come back to nuclear ideals.
To blow up. Ross?
Is there any initial thoughts on how you might put complementarity into this picture in the way that you did previously?
Well, I have, as I was just mentioning in the previous, in replying to Prakash's question, I have been thinking about recasting the way of doing observables in dagger categories, and I think there is an interesting different take on complementarity. And actually complementarity specifically, as one finds it in the literature, rather than maximally complementary or mutually unbiased operators, is a more general notion which we could discuss. So I think there's a lot of possibilities here. So there's broad answers, yes.
Okay, first Bob.
So why would we want to get rid of the task by writing down observables? Because that's
I
the
know,
whole point of introducing it is...
I know it offends your religious precepts. Bob recently has been giving talks called "In the Beginning God Created Tensor." So, no, it's a matter of it's just the usual Occam's razor argument that it would be strange if it was the only way of describing observables abstractly or algebraically use the tensor in a way because they don't appear in the primary phenomenology that one's trying to capture. You don't need tensor just to talk about observables. And in fact, a lot of the tensor structure is going to live. I mean, the kind of answer is that if you're interested in measurements, you're really looking at things like monads and comonads, as indeed in your work with Dushka. So then you really can look up into the functor category and monads there, and that gives you inherently a kind of monoidal structure there, without necessarily assuming it in the category you're starting off with. So that's a short answer.
Yeah, you could operationally say when you do a measurement, you always couple your system to something external. So there's always this idea of coupling.
I agree that the whole issue of how you delineate a system and then to make sense of it, really, the system, there always has to be an environment of the system. I entirely agree. But I mean, it's just to see what the minimal language is. And as I say, I think if one sort of starts to bring the functorial picture into account, you can actually find a lot of the structure you need by going up to the sort of functor category level.
But Bob, in the infinite dimensional case, you have the fact that a space may be isomorphic with a tensor product, which is true.
I can use this on the audience too, by the way.
Well, you should do it once.
Right. Okay, so lunchtime.